Hey guys, welcome to the 11th and last Cilk Plus tutorial of my Cilk Plus videos. Today we're going to be looking at breadth first search. But firstly, I just want to apologize about my previous videos' video quality. I'm going to try to make sure that this video is much better than my last video. I'm actually not too sure why the video turned out the way it did, but it was a very long video, so I really don't want to redo it. So just try to follow along as best as you can. I usually explain things while I'm doing them, so it shouldn't be too difficult. But again, if you have any questions, you can leave a comment or on either the YouTube video or on my um, tutorial website. But anyways, I'm going to try to make this video a little bit more short and sweet because this one is a lot more complicated. So I'm just going to go over the basics with you because I'm actually unable to compute any results on this computer anyways, mainly because of the fact that this computer that I'm using isn't the best computer and the fact that the code requires a certain format for the graph input, and I don't have MATLAB. I do have a MATLAB script that I'll provide in the video description, a link to, so you could download it. But if you have MATLAB, you can run the script and you can actually compile and run this algorithm yourself and you see how it works. But basically, I'm going to go through the basics of it. Um, so final step for the project, we're going to look at breadth first search. It's tricky in parallel. There's lots of papers on it, but we've picked this one paper right here. Um, so everyone should know that for sequential breadth first search, you usually use a queue for a two-visit type of list. In parallel, this is harder because you need to enforce some kind of mutex, in which case the alternative would be to use a bag data structure, which actually turns out to be one of our reducers in Cilk Plus. So these two guys from MIT describe it using the bag structure in Cilk Plus. It's kind of complicated, but they have a lot of pseudocode, and they actually their explanations actually make it pretty straightforward and simple. It's just when you get to the code, it gets really complicated. So I'm gonna skip most of the coding part and just go through most of the the basic stuff about it. So if we head on over to this link, it'll take us over to this page. So it's a 12-page paper which introduces the algorithm. It gives you a really good explanation in the abstract and the introduction. It goes straight into its results where it shows the speed up based on the number of processors versus different types of breadth first search algorithms. It gives you a simple serial implementation of breadth first search, the one that they're comparing it to, and then just dives right into the code and tells you about how they're doing it in parallel. So the parallel breadth first search routine does a parallel for loop. It also calls this process layer method right here, which is actually a recursive spawn and sync function, and we've already seen those before in merge sort. So yeah, give this a nice read. Here's where it talks about its bag structure. And the thing about the bag structure is that it's really complicated. It has penance. You have to have routines for union and split, and adding to the bag, removing the bag, splitting the bag. So all of this stuff is going to be in here for you to read. And then the rest of the paper basically talks about how they got their results, how it was different in comparison to other algorithms. Here they are. Here they are comparing breadth first search with depth first search. They talk about the non-determinism of reducers and the fact that there is actually a benign race, which is introduced in their original algorithm right here. See, they have a race, pretty much an inevitable race, which can give you an undeterministic amount of extra work. But they also give you an alternative to use a lock where you can resolve the race, but this would affect its runtime a little bit. So You could just deal with the indeterminism of the amount of extra time you might have. So this could be completely random every time you run it, or you can have it more deterministic, but you're guaranteed to take a performance hit. So this paper actually just gives you an option on which way to approach the problem. But then again, you should definitely approach it based on the type of data you're working with. Here's where they're talking about the bags again, and yeah, so these are all the different implementation they do. Where is it? Talks about scheduling. Where's the one where it talks about reducers? Yeah, okay, here. So here's a different alternative. So a modified locking protocol for managing reducers, which holds the lock for constant time. That's another alternative that it introduces. You can basically read about all of this. If you're really interested in it, you can read the entire paper. But if not, just read the abstract and the introduction, and then that'll give you a better idea of what it's showing you here. If you are, however, very interested, if you head over to the MIT website and you look up the parallel breadth first search algorithm, it'll actually take you to a page where you can download a paper where they're actually going through the design and the analysis of it. So here's the 12-page paper that just introduces and explains it, but here's a 77-page paper which gives you like the whole rundown on it. So it talks about how they thought it up. It goes into much more greater detail about the data structure that they're using, the bag data structure. It goes into even more detail of how they've compared their results to other results. So if you do have the extra time, go ahead and give this a read because it's pretty darn long. But yeah, that's pretty much it. Also, I'm going to provide this link where there's code